This is a question from the OCR paper in 2012. So it's quite an old question, but at the same time, it's quite a common concept that has come up in papers since then. I'm going to use it as a bit of a starting point. We're going to have a go at the question, particularly the calculations that are involved in it, and then we're going to explain a little bit further and come up with some more ideas about things that have come up in exams fairly recently. So first of all, if we read through the question, two cars A and B are crash tested by scientists. Car A has a crumple zone, but car B does not. Here is some information about the two crash tests. So it then gives us the mass of the car in kilograms, the mass of the driver in kilograms for A and B, and you'll notice that they're the same. The starting velocity of the car in metres per second, which is 20 metres per second for both cars, and the time taken to stop in seconds. For car A, that's 0.8 seconds. For car B, it's 0.2 seconds. So that's the only data that actually is any different. So straight away, that should be something that we should maybe consider talking about. Using the information given and by calculating the forces on the drivers, explain why a government might choose to make crumple zones a legal requirement. Okay, first of all, whenever you're given data in a question, generally in physics, you're expected to actually do a calculation with it. So that should be your first instinct. As soon as you see data or numbers of some description, whether it's in a table, whether it's within a question, you should be thinking, is there a calculation I should be doing? And here it actually tells us that we need to calculate the forces on the drivers, okay? So it's given us the mass, it's given us the velocity, and it's given us a time taken to stop. This is quite a lot of information. So let's leave the explanation for a little while and let's think about the calculations. So once you've written out, or once you've got all your information, mass, velocity, time, and force, the first thing that you should look at is your equation. So turn to the front of your booklet, and you should see that there's an equation for momentum, which is momentum equals mass times velocity. So we can find out the starting momentum for both the cars. Because the mass is the same and because the velocity is the same, then we know that the starting momentum for both cars is going to be the same. So let's think. We're going to use the mass, which we can see is 1,500 plus 80. So we're going to write that below where it says mass, and then it's going to be multiplied by the velocity, which is 20 metres per second. So if we do that on our calculator, 1,500 plus 80 obviously equals 1,580 times by 20, and this gives us a momentum of 31,600 kilogram meters per second. So we should know that as the unit of momentum. So that's the initial thing, and we know that this is going to be the same for both cars, regardless of the crumple zone, because the crumple zone doesn't actually affect the mass and it doesn't affect the velocity of the car. So the next thing is we want to calculate the forces on the drivers. And again, if you look in your equation booklet, you should see that there's an equation which is something along the lines of change of momentum equals the force applied times the time for which the force acts. So we want the force, that's what it's told us that we want to actually calculate, and we've got a time because that's what we're given in the table here. The change of momentum, if something is started at a particular velocity and is going to zero, so coming to a complete stop, the change of momentum is just going to be whatever the momentum is at the beginning, because it's going to be the difference between the start and the end momentum. Well, this is the start momentum. If the velocity is zero, it has zero momentum. So 31,600 minus zero is 31,600. So we could split this into A, and we could split this into B. So for A, we want change of momentum equals force times time. Let's make that look more like an A. Change of momentum equals force times time. We know that the change of momentum is 31,600. We want to know what the force is, and we know that the time taken to stop is 0.8 seconds. Okay, so if we want to actually calculate this, then we want to get F by itself. So we're going to divide both sides by 0.8. So we'll have 31,600 divided by 0.8 will give us the force. And if we do that on our calculator, then we get a force of 39,500 newtons is what's applied. Okay, so now I'm just going to change my pen colour so that it's a bit easier to see. So with B, we want to do the same equation. I'm not quite going to have space to write it out here, so I'm just going to write out the actual numbers below. So again, the change of momentum is going to be exactly the same. So 31,600 is going to equal F times, and our time taken to stop here is 0.2. So we're going to do the same thing again. 31,600 divided by 0.2 is going to give us the force. And if we do that on the calculator, then we'll see that the force is 158,000 newtons. So your first thing to do is to, so you've calculated the force on the drivers, you've already done that bit, fabulous. So now you need to use this information to explain why we might want to make crumple zones a legal requirement. Well, this is fairly obvious, really. We need to think about the fact that this force is bigger. And it's as simple as that. If there's no crumple zone, then the force is bigger. And that's stating the kind of difference between them. But you need to explain this a little bit more. So you need to basically link the fact that when there is a crumple zone, it increases the time taken to stop. Okay, so if we increase the time taken to stop, then we decrease the force. Okay, and it doesn't ever hurt to write because, and then to insert your equation, because change of momentum equals force times time. So by including that, you're showing mathematically that you know the relationship between these two values. Even though you've already done that here, it doesn't ever hurt to whack your equation in. And that goes for pretty much any explanation where you're using data to justify something. So the last bit, why might a government choose to make them a legal requirement? Well, here you're sort of stating the obvious by saying, well, why do we want to decrease the force? Well, if we decrease the force, there is a higher chance that you'd survive. So there's a higher chance of survival for whoever's in the car, and the government are in the business of keeping people alive, really, and less chance of injury. And so therefore, less cost to the NHS. Because if people are in car wrecks, then they have to go to A&E, they have to be patched up, they might have to spend time in hospital, and so that then costs money for the NHS. So we would want to decrease the force, mostly so that people live, but so that when they live, there's less chance that they're going to be injured, and therefore it's going to cost less to the NHS. So that's the basics of this specific question. But you also need to be aware that there are other scenarios that you get asked about in terms of momentum, change of momentum, safety, things like that. And they're ones I'm sure that you've learnt about. So there's crumple zones, first of all, and make sure that you know that it is a crumple zone and not a crumble zone. That's a really common error that we see. You also need to know about airbags. So airbags inflate, they act like a big cushion. They inflate before you actually hit the dashboard, and what that does is it increases the time taken to stop, so decreases the force. There's also seat belts that do a similar thing. seatbelts stretch ever so slightly, so that as they're stopping you, it takes a longer time for you to stop, and therefore decreases the force. So hopefully you're seeing a pattern in terms of the word that you're using. This is the biggest phrase really that you want to be using. We increase the time taken to stop. This decreases the force. So we've got airbags, seatbelts, and crumple zones in cars are the biggest things. Other examples, because cars are the most common example, car safety is the most common example that comes up in questions, but it can come up in a lot of other ways. So helmets, there's a squishy layer inside helmets, and there's also like a polystyrene type layer, all do the same thing. They increase the time taken to stop to decrease the force. There was a question a couple of years ago about a soft two like kind of sports balls, like I guess like a tennis ball and a squash ball, and if there's one that's softer, then it will take longer to stop, so therefore the force will be smaller. You have to be able to qualitatively talk about those sorts of things. Another thing is on playgrounds, they have like a squishy surface that's a little bit bouncy, and rather than kind of concrete or asphalt or what have you. And this playground surface does exactly the same job. Because it's a bit squishy, it increases the time taken to stop, which decreases the force. And all of this is because of this equation, that change of momentum equals force times time.